With this video, we're going to look at the modulus argument form for complex numbers, or representing a complex number in its polar form. Now, the form that we have been representing complex numbers in so far, this form here, a plus bi, we call that the Cartesian or rectangular form because it's reminiscent of a coordinate pair in the Cartesian plane. So we can think of it as representing a pair A, B, in R2 in the Cartesian plane, and hence we refer to it as the Cartesian or rectangular form. So what we're going to do now is we're going to represent it in polar form or in the modulus argument form. Right, okay, so we can think of as the complex plane is made up of the real part of Z, the imaginary part of Z. We know that the point Z can be represented as the real part A plus the imaginary part B times I. Okay, but we can also see that as having a point as having a radius, a value, a length to the point Z, and an angle it makes with the positive direction of the real axis. Okay, so the modulus of Z, the absolute value of Z, the modulus of Z, mod Z is mod A plus BI, is the square root of A squared plus B squared. I mentioned in a previous video something along the lines of this, and we could represent that as being Z times Z conjugate. Okay, so that would be the square root here of A plus BI times A minus BI, the conjugate. Okay, if you were to work that through, you're going to have the square root here. Well, we've done this before in previous videos, A squared plus BI minus BI, so that disappears. We're going to have here, I'll write it out, plus BI minus BI, and then we're going to have minus B squared, I squared. Well, working that through, remembering I squared is minus 1. What we have is A squared, they're gone. Minus B squared times minus 1 gives us plus B squared. That's a bit of annoying. Let me do that again. I overestimated that a bit. There we go. Okay, so another way of looking at it. Okay, anyway, so and this absolute value here, the square root of A squared plus B squared, is the radial length R. There are two arguments to consider. That's the angle it makes with the positive direction of the x-axis, positive direction of the real axis there. There are two, this is the angle, there is the argument, but there's two of these to consider. Okay, there's the capital A argument, the principal argument, okay, and that's the single value of theta in minus pi to pi range. Now remember that minus pi to pi, because it's inverse tan, because this angle in here is inverse tan of B over A, okay, and if I can just remind you here, if we've got this, if we're measuring in the counterclockwise direction, okay, that's 0, that's pi, okay, that's part of the interval, 0 to pi, and that's the positive direction. But if we were measuring in the negative direction here, then we go to minus pi. Okay, we're going from 0 to minus pi. That is, if you like, the negative direction there. Okay, so our principal argument is in that range 0 to pi or 0 to minus pi. Okay, if we've got something that's over pi, greater than pi, 5 pi on 4 for instance, then we're going to represent that as its negative value, minus 3 pi on 4. Okay, we're not going to, because that pass is greater than pi, we're then going to resort to the negative interval, and I will show some examples of that shortly coming up. Okay, because remember tan is periodic in pi, where sine and cos are periodic in 2 pi. Okay, so just be aware of that. It's from 0 to plus pi or from 0 to minus pi. All right. It's a semi-open interval in the sense that it includes from 0 to pi, including plus pi, but it goes from 0 to almost minus pi. Okay, otherwise the argument, because then the tangent function is repetitive, is cyclic like sine and cos, okay, and it repeats itself every pi. So there's going to be other arguments, as you'll see in other examples. So, okay, small argument A. Notice this had capital A, and the principal argument, and then all the others, we just write small a. Okay, that's inverse tan b on a plus 2 pi n. N belongs to the integers, so it'd be plus and minus. Principal argument theta is inverse tan b on a. All right, we just need to unpack that a little bit with some examples. All right, now just one thing, polar form. Each complex number can be represented by the ordered pair r theta. Okay, as we've seen, mod z is r, sine theta is b on r, cos theta is a on r. All right, some more things. Z is a plus bi, sorry, r outside of a on r, b on r, I, or r times cos theta, so cos theta a on r, plus sine theta I, sine theta b on r. If you have a look here, this r out front cancels the r's here and here, and so you've just got a plus bi. Nothing has changed. We're just playing games by putting the r in here. But having written it like that, we're now aware that sine theta is b on r. You can see that from the diagram above. If I would just go up here, sine theta is opposite on hypotenuse, b on r. Okay, so we're just playing around here, writing this out, and so we can write that as r times cos theta plus sine theta I. It's a little bit more of a compact way. Notice cos begins with c, sine begins with s, we have an I on the end. We can simply write that as r times cis theta, cis, cos, imaginary number, sine, because we can put the I just in front of the sine theta, and it is often written that way. So we get cis theta. Okay, let's have a look at some examples of this. Let's take the complex number z equals minus 3 root 3. Okay, so the real part is negative, plus 3i, so the imaginary part is positive. Okay, on the Argand diagram, that represents as minus 3 root 3 plus 3 here. Okay, so we're in the second quadrant there. Okay, well, let's find the modulus of z. That's this magnitude, this length here, r. Okay, so r is mod z, so we get the square root of negative 3 root 3 all squared plus 3 squared. That gives us 9 by 3 there. So negative 9 by 3, so it gives us the square of that, so it's 27, plus 3 squared is 9. Okay, and square root 26. All right, and r equals 6. All right, so principal value A arg of z is theta equals inverse tan 3 on 3 root 3. Okay, opposite over adjacent. Okay, but we're just taking the principal value. We're finding the value in the first quadrant. Okay, the principal value. Then we're asking ourselves, okay, which quadrant are we in? We're not in the first quadrant, which is over here to the right. We're in the second quadrant, and in the second quadrant, we know it's pi minus this value. Now, inverse tan 3 on root 3 is inverse tan 1 on root 3, which is from the exact ratios pi on 6. Theta is pi on 6. But we're in the second quadrant, so we therefore need, remember in the first quadrant, theta, and in the second quadrant, pi minus theta. So in that quadrant, we need pi minus pi on 6, which is 5 pi on 6. So this particular complex number, minus 3 root 3 plus 3i, is represented as z equals 6 cis 5 pi on 6. Okay? Now, okay, so that was straightforward. Let's move on now. Here's another one. Now this one now is in the fourth quadrant. So watch out for this. Watch out. It's the third quadrant, sorry. This is now in the third quadrant. So negative real part, negative imaginary part. We're now in the third quadrant. Remember I talked about tan going from 0 to pi or from 0 to minus pi. Okay? All right, so remember, all right. Anyway, let's start. First thing, r is a modulus of z, so same thing again, we're just going to have r is 6 as in the previous example here. Now we find the related first quadrant angle, the principal argument. The principal argument theta is inverse tan 3 on 3 times root 3 equals pi on 6. Okay, now in this particular case, our complex number doesn't lie in the first quadrant, so it's not going to be a part of our solution. Okay, but it's going to help us find the solution. Okay, we're in the third quadrant. Now in the third quadrant, the solution is pi plus pi on 6 is 7 pi on 6. Okay, remember here in the first quadrant it was theta when we're solving all these trig equations. Here it's pi minus theta, and here it's pi plus theta. But this is what you've got to bear in mind. Remember earlier I said we could only go up to pi in the plus direction or up to minus pi in the negative direction. Okay. We couldn't go over pi as we can with sine and cos when we're finding those solutions. So 7 pi on 6 takes us over. So it doesn't comply with the domain here. Okay. Now we can convert it by the following method. 7 pi on 6, if we subtract 2 pi, okay, that will give us minus 5 pi on 6. Now, minus 5, now if I had 5 pi on 6 plus 7 pi on 6, if I add them together, I'll get 12 pi on 6, which is 2 pi. Okay, complete circle. Okay, so if I'm going 7 pi on 6, then I'm going over pi. If I take away 5 pi on 6, okay, that's the same point. Okay, so if this one here is 7 pi on 6, then to get to 2 pi, the completely, this must be minus 5 pi on 6. Okay? I would go a complete revolution all the way around here if I had 7 pi on 6 plus 5 pi on 6 would give me 2 pi. Okay, so 7 pi on 6 is the same as minus 5 pi on 6. I can't emphasize that enough, so please be careful with that. That's our principal argument Z. And so our complex number here is Z equals 6 times cis of minus 5 pi on 6. Okay? That restricted domain from 0 to plus pi or 0 to minus pi must be taken into account. Let's have a look at another example. This time now we're going to be in the fourth quadrant. Let's move this down a bit. Okay, Z is plus 3 times square root of 3 minus 3i. So now we're in the fourth quadrant. Okay, this is the fourth quadrant. R is mod Z. Again, we're going to end up with R equals 6. Now find the related first quadrant angle. Capital A arg of Z equals theta equals inverse tan 3 on root 3, which is just 1 on root 3, which is pi on 6. Okay, and if we were in the first quadrant, if the question was, let's say Z was 3 root 3 plus 3i, if we were in the first quadrant, then this would be our solution. We would write Z is 6 cis, right, and we would have pi on 6. But we're not in the first quadrant. Okay, we're in the fourth, and in the fourth it is 2 pi minus theta. Okay, in the first quadrant it was theta. Okay, so here we are, pi on 6. So in the fourth quadrant, theta's solution is 2 pi minus pi on 6 is 11 pi on 6. But again, this 11 pi on 6 doesn't work. It goes beyond our domain, so we have to go back in the negative direction. Okay, well, to go back this way, all we needed to do was minus pi on 6. Okay, that's the same. 11 pi on 6 is going all the way around here. That's 11 pi on 6. Whoops, 11 pi on 6. If you add on a pi on 6, you get 2 pi. Okay, so here we are, 11 pi on 6. So so we converted by the following method: 11 pi on 6 minus 2 pi. Okay, gives you minus pi on 6. So we minus pi on 6 into the region there. Capital A arg Z. So therefore, our principal argument now is minus pi on 6, and we write Z as 6 cis minus pi on 6. Okay, and just finally, can I just stress that point again? The domain here matters. Remember, theta, capital principal argument, capital A, arg of Z, belongs to that domain. It is 0 to pi. Okay, it is, all right, 0 to pi in the positive direction. It is 0 to almost pi in the negative direction. Okay, and that's it. I think that's it, yep.